All right, so everyone, good morning. Okay, hi. So just a couple of announcements before we begin. I've updated my solutions. I've updated my solutions that are there on Moodle, so you can now find all the solutions up to and including chapter 4 there. So I'll put out the ones on the primes and congruences. Okay. Also, I'll be giving out at the end of this lecture. I'll be giving out the coursework. You see these new files that have appeared up here. I'll put a banner across them, but those are files that are relevant for the number theory part of the coursework. So I'll hand this out and I'll introduce it a bit to you shortly. Okay. But for the moment, we're going to return to where we were. So we're in chapter 4, dealing with congruences. We've introduced this congruence relation, and we've seen how when we consider the integer z modulo some modulus, this takes this infinite set of integers, infinite number of dots there representing all the integers, and it partitions the set of integers. Partition being a technical term, meaning it splits it up into a set of subsets, and there are n of these, okay, n of these subsets. And the nice standard representatives of these subsets are all the integers between 0 and n minus 1, okay? These smallest non-negative remainders that you can get modulo n, okay? And we've been dealing in this chapter with how the relation of congruence modulo n, how this fits well with the arithmetic operations that we have, okay? And what that means is, so this basically meant these statements here in 4.14, that if you took two congruent pairs, so A and A prime are congruent to another, so are B and B prime. So when you add A and B, you get the same result. You get something congruent to adding A prime and B prime. And the same thing for multiplication. When you multiply two integers A and B, rather than multiplying A and B, you can take two other integers, A prime and B prime, A prime congruent to A, B prime congruent to B. You multiply those, you get a different integer, but you get something in the same congruence class. Okay. So over here, we might have the A and the A prime. Over here, we might have the B and the B prime. When you add A and B, you land in some other congruence class. If you add B and B prime, you must land again in this same congruence class. Similarly, if you multiply A and B, multiply two of these integers, you end up in one of these other congruence classes. If instead you multiplied A prime by B prime, you can't land in any of the other ones. You have to land in this same one, the one that contains A times B. So A times B is in some congruence class, so is A prime B prime. A plus B is over here in one of the congruence classes, so is A prime plus B prime. What this means is we can actually view these operations of addition and multiplication. They actually become operations on the congruence classes themselves. So rather than seeing the integers as this set of infinite number of things, the infinite number of integers, when you introduce the relationship modulo n, you're shrinking it down to a finite set of congruence classes. Because you're lumping all these integers together that are divisible by n. These are the ones that are congruent to 0. You're lumping all the integers together that all leave a remainder of 1 when you divide them by n. All the things congruent to 1 modulo n, and so on. So how you write this in notation is we now have these operations of addition and multiplication that take place on the congruence classes themselves. The square brackets A here in this context is meaning the congruence class of everything congruent to A modulo n. Okay, so square brackets A stands for this whole subset here. Everything congruent to A. Square brackets B is this one. So we can actually talk about adding these two sets, and you get this one over here. Let's say you can talk of multiplying these two sets, you get this subset over here, the one containing A times B. Yes, question. Well, I haven't said exactly. They are any integers. So, but the point is, A and A prime are congruent to one another, modulo the modulus. Yeah. And B and B prime are congruent to one another. Okay. So I'm talking generally. I'm trying to explain this general picture. Okay, so this gives us our new way of looking at the integers. We select a modulus, and now the integers becomes this finite set of congruence classes, modulo whatever the modulus is. And we've got these two operations of addition and multiplication. Now this is what I started with last time. There already exists a mathematical framework for viewing situations like this, situations where you've got a set and an operation on it. And that's called group theory. And there's a whole third-year unit taught by me on group theory where we investigate these things in enormous detail and look at all the rich possibilities that there are in the universe of groups. But for now, we just really want to borrow some of the terminology and just kind of see it as the setting or as the kind of context where this kind of stuff goes on. But we looked at the definition of a group last time. So a group, we attach the name group to a set and an operation. So G is some set, star or asterisk is some operation or multiplication on the set G. It's a way of taking the elements from G, multiplying them together in some way. And these are the properties that a group satisfies, or that it's required for this set and operation to satisfy in order to be called a group. The set has to be closed under the operation. When you take two of the elements, you take the product A times B, it must still be in the set. That's certainly the case here. When you add two congruence classes, you get one of the other congruence classes. You take two congruence classes and multiply them together, you get another congruence class. The operation has to be associative. So when you take a triple product like this, it doesn't matter in which order you evaluate the binary products, okay? Because the operation you have is a rule for multiplying two things. When you got three things multiplied out like that, associativity says, well, A times the product of B times C is the same as the product of A times B times C. Existence of identity. So in order to be called a group, there must be a special element such that when you multiply it by any other element, you again get the same element back. So what's the identity for addition is what? Of congruence classes, and the identity for multiplication is what? Well, yeah, the identity for the multiplication operation is the congruence class of 1. When you multiply the congruence class of 1 by any other one, using the operation of multiplication, came from integers, it doesn't change the congruence class because you're only multiplying it by 1. Similarly, the identity for the addition operation is the congruence class of 0. When you add 0 to something, it doesn't change the other thing. Okay? And lastly, in order to be called a group, there must, for every element in the set, there must exist another element, A inverse. This is how you read A to the power minus 1. It's read as A inverse. Such that when you multiply A times A inverse in either way, A inverse or A inverse A, you must get the identity element. Okay, now, excuse me. the first operation we're going to consider, so we're going to look at whether the integers modulo n forms a group under the two operations, under the operation of addition and multiplication. We'll look at the addition operation first because it's the most straightforward. And the answer here is yes. So it does form a group under addition. So the set we're talking about, Zn, is the set of congruence classes. Okay, there are n of them. The usual standard representatives for them that we use are 0 through n minus 1. And we can check that all four of the group axioms are satisfied for this set. Okay, so that's contained in theorem 4.5 over here. You just need to check the various conditions. It's clearly closed. There is an identity element, namely the congruence class of 0. When you add the congruence class of 0 to any other congruence class, it's just the same as the other congruence class. Are there inverse elements around? Given any congruence class A, is there another one such that when you add it to it, you get the congruence class of 0? Well, yeah, that's simply the congruence class of the integer minus A. Because when you add those two congruence classes, according to the rule, the congruence class of A plus minus A, which is the congruence class of 0. Okay, so every element does have an inverse. Associativity follows from the associativity of the operation of addition on the integers, okay, from which the addition of congruence classes comes from. Okay, so it does form a group. Okay, so the integers modulo n under the operation of addition does form a group. Now, it's not a particularly complicated group. In fact, it's what we know in group theory is called a cyclic group. That means, so the meaning of a cyclic group is that it's generated by one of its elements. Because you notice about Zn, if you take the element 1 and you consider the congruence class of 1, congruence class of 2, which of course is 1 plus 1, congruence class of 3, 1 plus 1 plus 1, every element in the set can be generated from this one congruence class by just adding it to itself the appropriate number of times. Okay, so everything can be generated by using the operation on this one congruence class. Okay, that's what's known as a cyclic group, and they are particularly easy to understand, so to speak. One way of picturing what's going on in a group is to use the multiplication table of the group. In my time, when I was in primary school, this was a common thing to get them to occupy us, was to just write out the numbers 1 to 10 and on the side and 1 to 10 across the top, and just fill out all the additions and all the products and stuff as an exercise in basic arithmetic. Well, we can do something very similar for a group. So this is what's known as a Cayley table. Cayley was a British mathematician associated with some of this group theory stuff, so his name is attached to these things, but it's simply the operation table for the operation on the set. Okay. So here's the Cayley table for Z4, for instance, the integers modulo 4 under addition. So you have the elements down the side, the elements across the top, and in the middle, you're putting the sum, or using whatever the operation is, you're putting the product, but in this terms, it's this operation of addition of congruence classes, you're putting the product in that entry in the table. Now, for general groups, which might not be commutative, in other words, depending on what the operation is, it may be that A times B is, or I'll use star. It may be that A star B is not the same as B star A. Okay, if those are always equal, then the operation is called commutative. If they're not always equal, the operation is non-commutative. If you're familiar with non-commutative operations, matrix multiplication is non-commutative in general. Composition of functions in general is non-commutative. Okay, so things get very interesting, and there's a lot of interesting structure and hard mathematical problems when the operation is non-commutative. When the operation is commutative, it's a bit easier. So just to let you know the convention, when you're talking about Cayley tables for a non-commutative group, you have to be careful about, if you've got a group element GI here in the row heading and GJ in the column heading, okay, we're going to put the product of those two here. Well, you just have to say, well, which comes on the left and which comes on the right of the product. The convention is, the normal operating manner is to put the row index on the left and the column index on the right. Okay? I won't swear that that's universally true, that every book or source you look at will do their Cayley tables that way, but they should declare, they should declare the way they're doing it. But the convention we might use would be one like this. And this tallies with the usual convention about when you have a pair of indices referencing a matrix element. If I have a matrix M and I talk about the element or the entry in the matrix M23, which entry am I referring to? Well, it's normally taken that the first index refers to the row, second row, and the second index, 3, and then 2, 3, refers to the third column. And so it agrees with that. But however, in these modular arithmetic groups, we don't have to worry about that because the operation is commutative. So this GI star GJ is the same as GJ star GI in the groups that we're looking at. Okay, so here's what it is for the integers modulo 4 under addition. Okay, 2 plus 1 is 3. That's enough. 2 plus 3 is 5, but of course 5 is the congruence class of 1. Yeah, 5 is congruent to 1 modulo 4. So you can see all the sums modulo 4 there. You also quickly see that, it's not that hard to understand the structure of this table. And this is typical for cyclic groups. Across the top, you see, because we're using the identity as the first element, when you add the identity to anything, it doesn't change it. So the first row in the body of the table is simply a repetition of the column label. And thereafter, the next row is the same as the row above, shifted one place to the left. Shifted cyclically one place to the left, okay? Because the second row is 1, 2, 3, 0. And the third row, you just take that 1, 2, 3, 0, shift it one place to the left, and bring it down. And this one, which gets shifted off, reappears at the other end, okay? That is the structure that any additive modular group will have, okay? And so they're quite easy to understand. What's a bit harder or not so straightforward is the multiplicative ones. Okay. For a quick example, let's just get Sage to show us some. So Sage has got all these structures built into it, and I'll distribute a worksheet to you soon that shows basic commands. So Z15 I'm simply using as a variable name, and there's a command integer mod ring, which will come up now in the menu. So I press the tab key. Integer mod ring. So if I select that and I put in 15 as the modulus, what that creates is this ring of integers modulo Z15. And then I can then look at the Cayley table of the operation of multiplication. What I'm doing here is I'm typing the name of the variable and I type a period, and then I start typing the command and then press tab, and it shows me all the legal completions of that command. MATLAB has a similar feature. It's quite a common feature in computer systems. So I want to look at the multiplication table. It doesn't need any arguments, so just ask it for multiplication table. Now, that looks a bit weird for start because it's got the letters A through 0, whereas these are supposed to be the integers modulo 15. So what it's doing there is its default behavior. It's just using arbitrary labels for the elements, but that's not particularly enlightening in this example. So I need to force it to use the natural way of representing the elements as the names for the table. So there we've got the integers modulo 15. We've got the Cayley table for the operation of multiplication. Now remember, for multiplication, the identity element is 1. You can see that here. You take the number 1, you multiply it by any of these, you just get back the same thing. That second row there is just a repetition of the top row. Okay, so 1 is the identity element. Now remember, one of the axioms for a group said that every element had to have an inverse. Meaning for any element, there must be some other element that when you multiply the two together, you get back the identity element 1. Now you see that that's sometimes the case. For instance, for the element 8, when you multiply it by 2, you get 16, which modulo 15 is congruent to 1. So 8 and 2 are inverses of one another. Okay. You also see it for 11. What do you multiply by 11 to get the identity? Well, see 1 is over here, so you multiply it, you multiply it by itself. 11 is self-inverse. Okay. In the statement about the inverse axiom, there's no requirement that it's actually a different element. An element can be its own inverse. So 11 squared is congruent to 1 modulo 15. But some elements, for instance, if you look at the element 5 here, 5 doesn't have an inverse modulo 15. There's no element, none of these, which when you multiply it by 5, do you ever get the identity element 1. So there's that's a problem here. It's replicated if you look at 3, 5, 9, 10, or 12. None of those elements have inverses modulo 15. So as things stand, Z15 does not form a group under multiplication. Z15 does not form a group under multiplication. If you look at the bad, elements there, not a group under multiplication. So which elements are causing a problem? Okay, so some elements don't have inverses. Some elements don't have inverses. They are the ones that don't have inverses are 3, 5, 10, 9, sorry, skip 9, 12. 6 doesn't have one either. Okay, but all the others do. Whereas these elements do. And the elements that do have inverses are 1, 2, 4, 7, 8, 11, 13, and 14. Those elements do. Now, can you spot so these don't have inverses, these do. Is there another way to describe those two sets? So these are the bad ones. These are the ones that are not behaving in the group theory sense. These ones don't have inverses under multiplication modulo 15, but these ones do. But is there something else there that we can see?
Is it the factors of 15 that 15 splits into 3 and 5?
Yeah.
And all those other factors?
So we're talking modulo 15. 15 is 3 times 5. And you're right, all of these ones here have a factor of 3 or 5. Whereas these ones here don't. Okay, so 3 and 5 are not involved in the prime factorization of these integers, whereas they are in these. Okay. Another way to say the same fact is these are all the things which have a GCD with 15, the greatest common divisor of 15 of 1. So these are all the things that are co-prime with 15, whereas these are all the things, all the A's, if you like, for which the GCD with 15 is strictly greater than, have a non-trivial greatest common divisor. Now, if you look at any modulus, and you look at the multiplication table of it, I just got Sage to show me this just to save time, but there's nothing stopping you from generating these things. You know, they're not hard. It takes a long time to generate them if it's a big table, but there's no difficulty. You're just multiplying them out and reducing the products modulo 15. If you look at any other modulus, you'll always see this same behavior. Okay, it's the ones that are co-prime to the modulus, they have an inverse, but the ones that are not co-prime don't. Okay. So that immediately gives you a conjecture. So we would wonder, is that true in general? And it is. Okay. So there's this question. So we look at some examples. We see there are lots of elements there that don't have inverses. We might look at a few examples. We might spot it's always the ones that are not co-prime to the modulus that cause the problem. So we suspect that that's true in general. So if we examine it in general, we'll find that it is. Okay. So here's the general argument. We're dealing with the modulus n, and we're dealing with an element a, and we're wondering, is there an inverse for a modulo n? Okay. Is there another element such that when you multiply it by a, you get back to 1? Is there a b such that when you multiply it by a, you get 1 modulo n? B would be called the inverse of n. Okay. Some of the time there is a b. These ones have a b, and it's always one of these other ones. It's always drawn from the same set itself. These ones don't have a b. Okay. So what's going on? Well, if you look at, we start examining this. So here's the statement that a has an inverse. There exists a b such that ab is congruent to 1 modulo n. And we examine this in general using what we know about congruences. Well, we just unravel the definition of congruence. That means there exists a b such that n divides the difference ab minus 1. And we unravel, what does it mean that n divides the difference ab minus 1? Well, that's the same as saying there exists a q such that ab minus 1 is q times n. So we got this double existential, this statement, ab minus 1 equals q times n, and a is some fixed number we're investigating, n is the modulus, b and q are parameters, and they're both existentially quantified. There exists a b in z, there exists a q in z such that this is true. A simple rewriting of this equation turns it into this, that 1 is equal to ab minus qn. So what we're saying is a has an inverse if and only if there's a linear combination of a and n that's equal to 1. That's what we were able to, using the definition of congruence and divisibility, that's how we rephrased the equation, the question in an equivalent way. A has an inverse modulo n if and only if there exists a linear combination of a and the modulus n that's equal to 1. Now, the existence of linear combinations of a pair of numbers equal to 1 by a previous exercise, back in chapter 2, that's the same as saying the greatest common divisor of a and n is 1. Okay? So all these movements here from one form to another, they're all equivalences. They're all true. Each one is true if and only if the other one is true. So we have indeed proved this conjecture. The only a's that have inverses are the a's that are co-prime to the modulus. Okay. So that's this theorem 4.6. Okay, the congruence class A modulo n has an inverse with respect to multiplication if and only if the GCD of a and n is 1. Proof of it is there in that paragraph. So then this, because these are the only ones that have inverses, if we want to think about, is there a group under multiplication here, we have to chuck out the ones that don't have inverses. Okay, so there is a group under multiplication modulo 15, but it isn't all of the possibilities modulo 15. It's only the ones that are co-prime to 50. Okay. Okay, so that's kind of contained in this theorem 4.7 and definition 4.9. Again, just introducing some more terminology. Standard terminology for this is the reduced residue system. Okay. When you look at Z modulo 15, and you think of all the integers 0, 1, 2, of course 0 was another one that didn't have an inverse there. Okay, the integers modulo 15 are all of the numbers 0 through 14. That's a complete set of representatives of the congruence classes. Or another way of terming it is that these are all of the residues modulo 15. All of the small remainders that you can have left behind after you divide by 15. A reduced residue system is where we take this complete residue system and reduce it. And we reduce it by chucking out the ones that aren't co-prime to 15. That aren't co-prime to the modulus. So the ones we're left behind with are the set of all the congruence classes. We're being a bit hazy about whether we're talking about a set of representatives or a set of congruence classes. Really, we're talking about both. It's a little bit ambiguous. But it's the set of congruence classes or the set of residues, if you like, that are co-prime to the modulus. That's the reduced residue system. And this set, under the operation of multiplication, does form a group. Okay. This will satisfy all the group properties. Okay. There's a couple of examples. If we look at the top of the page of Z5 and Z8. So these are the multiplicative groups of integers under multiplication modulo 5 in the first instance and multiplication modulo 8 in the second system. You notice for 5, because 5 is a prime number, the only one of the standard residues that isn't co-prime to 5 is 0. 0 is divisible by 5, of course. Okay, but none of the others, all of the others are co-prime to 5. So we've got, it's complete as possible for say 5. And of course, that's the same whenever the modulus is a prime. Whenever the modulus is a prime, in the multiplicative group, you're going to have all of the integers 1 through p minus 1. Here, 8 is 2 cubed, so it doesn't contain any of the even integers between 0 and 7, but it contains all the odd ones. Okay? Now, these Cayley tables are not so simple as the additive ones. There's no kind of easily said way of saying that one row is just a simple shift of the row above it. I don't think. So the structure is a bit more interesting here, in that it's not so easy to describe. Okay. So the multiplicative groups are, as to be expected, because this is all tied up with the operation of multiplication, and we know very soon there you get to the concept of prime numbers. The multiplication operation is a bit more mysterious, or has a richer structure. Okay. Now, I'd like to just switch to the overhead to do something now. So in the tutorials, we examined problems about simplifying powers modulo n, modulo something. Okay. We looked at a to the power b is congruent to what? Modulo n. And what we found in the tutorial was we could investigate we could investigate powers of A modulo n and find they went round a cycle. Went round a cycle of values. So you had a to the power 0, which of course is congruent to 1. Then you had a, then you had a squared was something, and a cubed was something, and yada, yada, yada. Eventually you got back to some power of a, which was, so this is a to the power m. Sorry, to be clear, a to the power m for mother. A to the power m, which brought you back to the start, which was congruent to 1 again. Okay, so this cycle has m steps in it. So the first step, second step, third step, and the last step is the nth step, which takes you back to 1. And then we could use the cycle length m to break down the original exponent b. So all we needed was b modulo n. And we found that a to the power b was congruent to a to the power b mod m. And this was modulo n. Okay, so, well, basically, I'm just setting up tomorrow's lecture, really. This problem of finding the cycle length for a general element will occupy the next few lectures. And there's a problem or two in the coursework that is based on. And the natural setting for this problem is the group, is the multiplicative group of the reduced residue system of congruence classes modulo n, chucking out all the ones that are not coprime to n. Okay, so just to end with, so I'm going to hand out the coursework, and I'll just introduce it a bit and say a few words about it. You will also find on Moodle an electronic copy of it, which I'll put up afterwards. PDF copy of this.